So peptides to protein. So I kind of already alluded, length is our key difference here. Okay? A peptide or polypeptide, we're talking about a chain of about, maybe your book uses 50 residues as the approximate cutoff. Okay? This is typically sort of unstructured and might not have a repeatable fold kind of associated with it. Okay? A protein, on the other hand, sort of the name protein, is reserved for our longer chains, and they adopt some regular secondary structures. What are the secondary structures that we know of? Alpha helices and beta sheets. Lovely. What do you think is the longest length for a protein? What's the longest protein we have in the body? You don't have to name it. I'll name it for you. If someone knows it, awesome. But how long is it is my question to you. How long do you think it is?
15.
15 what?
The muscle one.
It is in muscles, but 15 is not a number that I'm looking for. 15,000, is that your guess?
Yeah.
Longer. Any other guesses? 30,000? 30-ish thousand is the answer. It is a protein that's in the muscles. And anyone want to give it a name? Guess? It's a really appropriate name. It's called titin, which I think makes sense. It's big. I don't know, titin. I don't know where that came from, but it makes me think of. That's at least how I pronounce it. Doesn't really look like much in the ribbon structure here, right? Like there's nothing about this structure that indicates to me that it's as many as 34,000 amino acids long. So this is a ribbon diagram. I may use them. What is anyone who's already familiar? This arrow, what type of structure is that referring to? A beta sheet. And a helix looks like an alpha helix, and then these like long regions that don't look like anything. Those are our unstructured pieces, our loops, our whatever, linker sections, whatever you might want to call that stuff. Okay? So here we have sort of all the way out from you have a bone. Connected to it is your muscle via a tendon. And then we have these bundles of muscle fibers and goes all the way down. Again, if you've taken an anatomy or phys class or you got this in a bio class, cool. Detail I don't care about so much other than to show you where this protein is acting here. Okay. This first link here has a couple of nice infographics about how titin behaves in the muscle. This next link here is a paper it's a biomimetics paper trying to create a synthetic polymer based on how this actual protein functions. Okay? So several of these can sort of link up together to have, create, individual titin proteins have like piconewton force that they can generate, which really isn't much, but how they connect to each other and how they do that, can we scale that up to a more macro scale? So a really interesting paper, and it's a really short read too. It's like 2 pages, 3 pages. So just for you if you're interested. I think I limited what mimetic principles you could pick for your extra credit, just to make it easier for me to get through, rather than letting you guys like go off the rails with anything you could find that I'm not familiar with yet. So this wasn't a choice, so you can't pick that paper. Okay. Is the protein backbone polar? Yes or no? I gave you the picture. Yeah, right? So we said the amide nitrogen can serve as this H bond donor. Our carbonyl carbon, that oxygen, might serve as an H bond acceptor. So we have polarity in the backbone itself, right? The backbone itself wants to be able to make hydrogen bonds. And the fact that the backbone needs to make hydrogen bonds is really what governs the formation of the secondary structures. It's to satisfy backbone H bonds, okay? Not the side groups, right? You could have a string that's all non-polar hydrophobic side groups. There's no H bonds for those there, and that stuff's still gonna make alpha helices or beta sheets because those things arise so that the backbone can satisfy its H bonds. So the two primary structural elements, primary secondary structural elements. I probably wanted the word secondary here. okay? The two sort of secondary structures we think of are the alpha helices and beta sheets. And like I said, the reason they exist, at least in part, is so that that backbone can satisfy the H bonds it wants to make. And in order to be able to satisfy those backbone hydrogen bonds, we can't guarantee what type of side groups we have. There might not be something that can make a hydrogen bond for us on there. Like I said, it could be all hydrophobic stuff. So in order to satisfy those H bonds, the backbone is going to hydrogen bond with itself, okay?